Think about a typical sixth grade math problem today, maybe adding two fractions or multiplying two-digit numbers. It is straightforward. You learn the steps, apply the rule, and find the answer. Compare that baseline to problem 438. This is a massive, multi-layered equation crammed with nested brackets, division, and an isolated variable. While this appears to belong in an advanced algebra class, it was actually assigned as basic arithmetic. It comes from a textbook by A.F. Malinin and K.P. Baranin. Their collection of arithmetic problems was standard issue for secondary schools in Imperial Russia. The table of contents moves from numeration through whole numbers, fractions, ratios, and the rule of three. Formal algebra is entirely absent from the curriculum. Dropping this massive cognitive load into an arithmetic class was a deliberate pedagogical strategy designed to engineer mathematical minds. Today, we often view arithmetic as a rote discipline, the memorization of times tables and the mechanical execution of long division. Malinin and Baranin had a different objective. They used arithmetic to build raw cognitive stamina. By withholding formal algebraic formulas, the text removes standard mental crutches. Students must hold multiple interacting relationships in their minds simultaneously. Restricted to addition, subtraction, multiplication, and division, the brain is forced to construct deep mental models of functional variance and algorithmic isolation. Examining this text reveals how deep cognitive capability is developed through extreme constraint. The foundational training ground for this cognitive load is the word problem. These students were expected to calculate multi-step logistics for a rapidly expanding 19th century society. Problem 253 asks students to calculate water flow into a basin with a capacity of 61 barrels. 3 separate pipes are active, 2 flowing in, 1 flowing out. They run for 5 hours and 40 minutes. The student must determine the remaining volume needed to fill the basin. Modern students might reach for a system of equations, but these students had to solve it without relying on a formalized algebraic variable. First, 61 barrels must be converted into vedros, holding 2,440 as the capacity ceiling. Next, they track 3 flow rates, plus 3 vedros a minute, plus 6, and minus 2. Then they apply the total time to that net rate. This creates a severe cognitive burden. The student is constantly balancing unit conversions while actively tracking opposing flow rates. The answer requires unbroken sequential logic, finding a net flow of 7 vedros per minute, calculating the total volume, and subtracting it from the 2,440 vedro capacity. Without a formula to lean on, the student relies purely on working memory. This serves as essential training for algorithmic thinking. Later, the curriculum moves from concrete scenarios to purely abstract number relationships. This pivot occurs in Chapter 2, Section 9, which focuses on changes in the product and quotient. Problem 348 asks, what will happen to the quotient if we increase the dividend 15 times and decrease the divisor 3 times? This doesn't ask for a static number. It demands an analysis of a rate of change. Visualize the dividend as a solid mass and the divisor as a grid slicing it. The first operation scales the total mass 15 times. Decreasing the divisor by 3 makes the grid finer, creating slices 3 times more numerous. These changes compounding, resulting in an output 45 times larger. The student is effectively manipulating the functional variance of an algebraic equation without learning symbolic algebra. This method represents a pre-algebraic functional thinking. Teaching proportional reasoning before introducing symbolic variables ensures that the student truly understands the underlying logic of how values behave. Mentally tracking how shifting values impact one another is the exact cognitive intuition required for limits and derivatives in calculus. This curriculum scaffolds that intuition using only the basic language of multiplication and division. Under Malinin and Baranin, arithmetic is a dynamic system of relational mechanics. This leads us back to the massive equation from the start of the video. These equations appear in Section 11 as the ultimate culmination of the curriculum's conditioning. The unknown variable x arrives as the natural outcome of the functional thinking they have practiced for hundreds of pages. In Problem 427, the student must solve for x without algebraic graphing tools. The technique requires identifying the outermost operation to dismantle the structure. The student inverts the operation, subtracting 7 from 7,200, which leaves 7,193, and strips away the outer bracket. They systematically invert the division, multiplication, and subtraction, peeling the onion until the variable is isolated. Executing this multi-step isolation requires extreme structural discipline to avoid a single error in operations. This requires no new mathematical skills. It simply pushes the fundamental tools of arithmetic to their conceptual limits. The curriculum proves a distinct pedagogical philosophy. Modern approaches often rush students into abstract algebra before they have mastered concrete logical dependency. Rigor is built by stretching fundamental tools to their absolute conceptual limits. The complexity of these problems reflects the intellectual capability expected of students over a century ago. By utilizing arithmetic as a dynamic system of relationships, Malaninen and Burinen engineered a powerful framework for rigorous mathematical thought.